Alright, so now let's talk about equilibrium. Now, equilibrium, and one of the plain definitions of equilibrium is when the rate of the forward reaction equals the rate of the reverse reaction. That's all equilibrium really is. And if you think about the definition of equilibrium, just like the plain out definition of equilibrium, then you automatically think of balance. And when talking about equilibrium, I always think of a seesaw. So if I drew a seesaw over here, and if you ever use a seesaw, then you know that there's always a balance. So when you're both at a certain weight, when you're both like maybe 150 pounds, if there's 150 pounds on both sides, then this would be an equilibrium. So if I wanted to rotate this a little, this would be at equilibrium. So both sides are pretty much the same. It's in balance. That's when you're in equilibrium. So equilibrium is basically balance. And I want you to remember this seesaw when we're talking about equilibrium entirely. Think of the seesaw as going up and down, because when the seesaw is in balance, that is when we're sort of in equilibrium. You could think of the seesaw example as being in equilibrium. Now, if you wanted to see equilibrium from an actual graph, it would be something like this. So I'm just gonna draw this square right here and use my eraser to draw a little graph over here, and this is gonna really illustrate what equilibrium looks like. So let's just say we had two compounds, and the I guess you could say the formula would be I think it's N2O4. So decomposition of N2O4 goes to 2NO2. So I believe that's the equation that we're going to be using. And let's just say blue represents our N2O4 and red represents our 2NO2. So if we looked at a graph of seeing the concentration of the reactants and the concentration of products, because over here this is our reactant, over here this is our product, so all we have to do is draw a little curve right there, little exponential curve right there, and this represents our concentration. So I'll put N2O4, and over here is our concentration. So I'll just put CON just to say concentration, and over here is time, and let's just say time is in seconds for this example. Just throwing out an example out here. I really wanted to illustrate what equilibrium looks like on a graph. So this is our N2O4. Reason why the concentration is decreasing is because we are going from reactants to products. And when that happens, we're losing concentration of reactants in order for those reactants to turn into products, in order for the concentration of the products to increase. And this is what it would look like on the graph. So it's kind of like the antithesis of the reactants, and I wish I had sort of a straight line over here, but this is our N2NO2, so 2NO2, and right over here, right at this mark, this is when we're in equilibrium. So we are in equilibrium. More specifically, we're in dynamic equilibrium. So dynamic equilibrium is this idea that the molecules are still moving. We haven't stopped the entire reaction. The rate of the forward reaction is still going, the rate of the reverse reaction is still going. So we're still having a rate of forward, so we're still having reactants turn to products, we're still having products turn to reactants, we're still having this idea, and maybe I should draw a double arrow here since it's equilibrium, but when we're in dynamic equilibrium, the molecules are still moving. We haven't stopped the reaction. The only reason why it's, I guess you could say, stalemate, or they're kind of in equilibrium, is because the rate of the forward reaction equals the rate of the reverse reaction. meaning that we're making as much products as we're making reactants and vice versa. So rate of the reverse reaction equals rate of the forward reaction. That's when we're in dynamic equilibrium. The reaction doesn't stop, it's still going, but we're in equilibrium. So now that we know that, we should talk a little bit about the reaction quotient. So reaction quotient. And our reaction quotient is denoted as QC. So this is our reaction quotient. And reaction quotient is basically when you are pretty much finding, and reaction quotient looks something like this. So if we bring back our N2O4 example, and I'm just going to put double arrows over here since they're in equilibrium. So it's N2O2. Our reaction quotient is products over reactants. So this would basically be NO2 squared over N2O4. And that equals our reaction quotient. Now you might be wondering, well, why is NO2 squared? Well, when we're finding the reaction order, we look at the stoichiometric coefficients, because our stoichiometric coefficients really determine the reaction order for reaction quotients. So if we had like a 3 over here, and this is not true, this is just throwing out an example, but if we had a 3 over here, then we just put that to the power of 3. And if instead this wasn't a 2, and this was maybe like a 7, and like I said, we're just throwing out examples over here, not realistic, just throwing out examples, then this would be to the power of 7. So your stoichiometric coefficients really matter when trying to find your reaction quotient. And whatever that stoichiometric coefficient is, that's what you put it to the power of. And that's pretty much reaction quotient. Now, it's important to know reaction quotient because we relate that to the equilibrium constant. So our equilibrium constant is usually going to be Kc. If it's pressure, it's going to be Kp. But that's our equilibrium constant. And pretty much as the name says, this is just our constant equilibrium. But when we're relating reaction quotient and equilibrium constant, this is when we really know when it's in equilibrium or whether the reaction has to shift from the right or to the left. Meaning that, does the reaction need to produce more products in order to get back into equilibrium, or does the reaction need to produce more reactants to get back into equilibrium? So when we're in equilibrium, QC is going to equal Kc. So our reaction quotient is going to equal equilibrium constant. Now, this isn't all the time where our reaction quotient will equal our equilibrium constant. Because sometimes our reaction quotient could be smaller than our equilibrium constant. And when this is the fact, when we have a reaction quotient that is smaller than our equilibrium constant, then this basically tells us that there are more reactants than products. So if we have more reactants and less products, then the reaction is going to shift to the right to create more products so we can get back into equilibrium. So let's go back to that seesaw example real quick. So I'm just going to scroll down over here. Let's go back to that seesaw example. So over here, let's just say we have the reactants on the left hand side. So I'm just going to denote this as R. So R is our reactants, P is our products. So when QC is less than Kc, when our equilibrium or reaction quotient is less than our equilibrium constant, then we're going to have more reactants than products. And when this happens, in order to get back to equilibrium, in order to get back to our normal seesaw, so our normal seesaw is when we had, let's see, when we had something like this, and just gonna try to make this a straight line. But when it's something like this, that's when we're in equilibrium because we're balanced out. Our reactants equal our, or the sort of reverse reaction equals our forward reaction, but we have a similar amount of balance. So when we have more reactants than products, the only way to balance that or to counteract that is to move to the right, to create more products from those reactants. Think about it. If we have a bunch of reactants, and I'll put 1, 2, 3, 4, 5, 6, and over here maybe we only had 2 products, so reactants, products, and we want to get back to equilibrium, well, we're going to have to create some of these reactants to products. So reactants to products, and until we're in equilibrium, so 1, 2, 3, 4, 1, 2, 3, 4. So the reaction has to go to the right. It has to shift to the right because we have more reactants. And another way you could memorize this is with this, I don't know what you call it, maybe like an arrow or something, half an arrow. I really don't know what you call this little thing, maybe like less than. So when you have this thing, think of it as the crocodile. So I just put a little teeth there, not the best teeth, but the crocodile will eat the direction. The crocodile will go to the direction. So since it's eating the equilibrium constant is on the right, so the reaction will shift to the right. So it's just something this small to sort of remember, and this might help you understand which way it might go, which way the reaction is going to shift. So I always think of this crocodile, wherever that crocodile goes to eat, that's where the reaction will go. That's where the reaction will basically shift. And remember that Q comes before K. And the only way for this crocodile analogy to work is if Q comes before K. So you could, one way I remember this is every queen needs a king. So every queen needs, or I spelled queen wrong. Every queen needs a king. So every queen needs a king. And when you write that, Q and K, whichever way that alligator is eating, that's where the reaction is going to shift. So if we look at another example, let's say our QC is greater than our KC. So our reaction quotient is greater than our equilibrium constant. Well, if this is true, then that means we have more products. So the reaction is going to shift to the left. And let me just write this over here. Shift right. Just to have this as your notes. So shift right. But the reaction is going to shift left because when we use our analogies again, the crocodile analogy, having a little teeth over there, crocodile is going to the left, so reaction is going to shift to the left. Because we have more products, so we just have to flip this over. If we have more products, then the only way to get back to equilibrium is to create more reactants. So going reverse, creating all those products and turning them into reactants to get back to equilibrium. Alright, so let's look at this practice problem right here. So it says that the equilibrium constant for this reaction is 5 times 10 to the negative 3 at a certain temperature, and equilibrium concentration of nitrogen, hydrogen, and ammonia found to be 0.1, 0.3, and 0.2. And let's just say this question was asking us the reaction quotient and also which way the reaction would shift. So we obviously need to find the reaction quotient and relate it to our equilibrium constant. So to find our reaction order, all we really have to do is use our formula, products over reactants, with the stoichiometric coefficients being the whatever the molecule is to the power of. So for this example, it would be, we have, oh, not 2 there, we have NH3 squared over, and we have N2, and then times hydrogen gas to the 3rd power. So this is our reaction quotient. That's a formula that we're going to use. And if we plug in our numbers, our ammonia was 0.2, so 0.2 squared over, and our nitrogen was found to be 0.1, and our hydrogen was found to be 0.3, but to the 3rd power. So if we do that math real quick, so it's going to be 0.2 squared over 0.1 times 0.3, that's cubed. So we're going to get 14.8. I'm just rounding over here. And 14.8 is definitely less than 5,000, because 5 times 10 to the third power, I believe that should be 5,000, right? Yeah, so it's 5,000. So this is our reaction quotient. This is our equilibrium constant. So as you can see, our reaction quotient is much smaller than our equilibrium constant. And if we remember the crocodile analogy, that crocodile is going to the right and the reaction is going to shift to the right, since there are more reactants than products, because our reaction quotient is much smaller than our equilibrium constant. I don't know if I discussed this topic, but it's good to know that if our equilibrium constant is much greater than 1, then we're going to have more products. So more products, and if our equilibrium constant is much less than 1, then we're going to have more reactants. So this is something good to know. So when you're going to see some problems where it might give you some sort of graph, or it might show you the K values, and it might ask you, are there more products or reactants at equilibrium? And if you see that the K, that equilibrium constant, is much greater than 1, or even just greater than 1, there's going to be generally more products than reactants. And if you see a K value that's like 0.001 or 0.00001, then you're going to see more reactants than products.